All right, this chart will introduce friction. So some top-level points first. If you have an object sitting on a table, for example, we know there's a normal force acting perpendicular to the table if the object is in a gravitational field or it's being pushed down by something. Friction now acts not perpendicular but parallel to the surface on which little m sits. Um, it's also proportional to whatever the normal force is. And you should note that the normal force is not necessarily always equal to mg. If the object, if m is sitting on a slope, for example, theta is not equal to 0. It's on an inclined plane. The normal force is smaller than mg. If it's sitting on a level surface, but there is somebody pushing down on top of the object, well, then the normal force is going to be bigger than mg. Okay, thirdly, there's two kinds of friction. There's static and kinetic friction, but essentially, if you push on an object, and you know this from your own personal experience, you can increase the force with which you push on the object. To make things simple, let's say you're pushing horizontally or parallel to the surface, if the surface is horizontal. And you can push and push, you can keep increasing the force, but it won't move. It won't move until you get up to a maximum force. And the little sub s means uh, static. Static means it's not moving. And so once this maximum frictional force is exceeded, then it starts slipping. Slips, in other words, when F sub s, the frictional force, is equal to this max force. And then one immediately transitions to kinetic friction. All right, so the um, simple modeling equation is that for both static and kinetic friction, static means it's not moving or just about to move. Kinetic friction means it is moving relative to the surface. You have a constant of proportionality called the coefficient of friction, mu sub s times the normal force for static, mu sub k times the normal force for kinetic. And because the kinetic frictional force is smaller than the static frictional force, mu sub k is generally smaller than mu sub s. I say it the other way around here. Mu sub s is bigger than mu sub k here. Mu in general depends upon both surfaces. Wood to wood, wood to steel, glass to steel, aluminum to glass. That's the way, a simple way to model it. All right, so let's take an example here, if we can. Let's say Carol pushes a 50-kilogram wood box across a wood floor. So wood is going to define what the coefficients are, static and or kinetic. We would look it up in the table in your book. She pushes this 50-kilogram wood box across a wood floor at 2 meters per second, constant velocity. What force is required by her to maintain this constant V? And if she stops pushing, how far does the box move? All right, so the first scenario is one of here's a motion diagram. So this is constant velocity. Well, by Newton number 2, that means the net force has to be 0. And so here's a force diagram. I have endeavored to draw all the y forces to indicate that they sum to 0. So the normal force is equal and opposite to the gravitational force. And the frictional force acting opposite the motion is equal and opposite to her push in the direction of the motion. And so bookkeeping that with an x and y equation, Fp minus F sub k, F sub k because the box is moving, equals to m times a sub x, but since the velocity of the box in the x direction is constant, that's 0, which means F sub p, that's her push, is equal to, in magnitude, to the frictional force, but from the modeling equation above, that's equal to the coefficient of kinetic friction times the normal force. The normal force we're going to get out of the y equation. This is a general thing you'll see in friction. So the y equation for this scenario is n minus mg is equal to 0 because the y acceleration is 0 and therefore n is equal to mg. Well, now we can go back and plug that into here. F sub p is equal to mu sub k times n. 0.2 is out of your table in the book for wood on wood for kinetic, times m times g, so that's 50 kilograms times 9.8, and so that is 98 newtons. On the other hand, if she immediately stops pushing, then because there is only one horizontal force now when it's opposing the motion, the motion diagram is going to look like this, which of course represents a delta V pointing to the left. That's an acceleration pointing to the left, consistent by Newton's second law with the net horizontal force pointing to the left. So the x equation gives us minus fk is equal to m times a sub x. And the y equation, as before, gives us n equals mg. And so the x acceleration from the first equation is minus s sub x over m, but through the same mechanism as we did in the first part, f sub k is mu sub k times mg minus, of course, divided by m. So the m's cancel, and the acceleration in the x direction is minus the kinetic coefficient of friction times g, which is minus 0.2 times 9.8 meters per second, minus 1.96 meters per second. So if we know what the initial velocity is, and we know what the acceleration is, and we just figured that out, number 2, we can use our kinematic equations with constant acceleration, in particular equation number 3, to figure out what the displacement is that this box undergoes in the process of stopping. And so we would set v sub x equal to 0 meters per second. V of x naught would be its initial velocity, which is 2 meters per second. Both of these things get squared, and then on the bottom we have 2 times a sub x. Please note that there's a cancellation of minus signs here, and if you go through this, you get 1 meter. I'm going to double check that here. It's 2 divided by, it's 4 divided by 2 times 1.96. Yes, it's very close to 1. 1.02, it rounds off to 1, to 2 sig figs.